First of all, I just wanted to point out on CRAN, we have our BART package. We're up to version 1.3. A lot of the stuff we're talking about today are not available in 1.2, so you really need the latest and greatest. Rob's original article is right here. It's a free. It's available for free. And then our article on survival analysis is right here, and it's technically it's not free, but Statistics in Medicine put it up as an online teaser, I guess, or something. So it's available for free until they change their minds. All right, so first I wanted to talk about computing with BART. Here's an outline. Actually, I'm just going to skip the outline. Okay, so like I said, our current package is on CRAN. The latest version of R, I find, has a quirk in it. I don't know if anybody else has noticed this. But in 3.40, which is the version that I'm using, it doesn't seem to have a definition of a personal library. There's only a global library, and you may or may not be able to install into the global library. But there's an easy trick here. You can create an R profile for yourself and just put this command in there, and that'll create a definition for your personal library, and then you can install into that. So I don't know if everybody's done this. Okay, raise your hand if you've installed the BART package. So not very many of you have, but it's actually not that hard. It only depends on one other package, RCPP, and it's basically a one-liner. Also, I might add that since we put the BART package online in April, we're around 2,700 downloads already. So it's I'm not saying it's the most popular package ever created, but we were very surprised and very pleased by the number of downloads we've gotten so far. If you're a Unix or a Linux person, and when I say Unix in lowercase, I mean Unix, Linux, Mac OS. So you can install this easily from the command line. It requires a full C++ tool chain. It works with both new GCC or Apple Xcode. And so this is what it looks like. You have this options command. You tell it which CRAN repo you want to use, and install BART with dependencies equal to true. So that way it'll install RCPP and BART at the same time. And I think I'll take questions as we go. That way we won't be in a big crunch at the end, okay? All right, so there are actually 4 BART R packages on CRAN. There's Base Tree, which Rob mentioned. That was Rob's first package, but it's sort of fallen on hard times. We're not updating it anymore, and it's actually written in a way that makes it a little tricky to update. But it's there for historical purposes. We're probably just going to be there forever. But I'm not sure how many people are using that versus the more modern packages, which are generally much faster. There's a package called dbarts, done by Vincent Dory at NYU, and it's fairly fast. It's probably the fastest. but fast comes with some consequences, as we'll get into. BART is not as fast as dBART's, but it's much, much faster than BART machine. Rob touched on this. The computer language that BART is written in is C++. That's also true of dBART's. And unfortunately, BART machine is written in Java, which is kind of a nightmare if you're an R user. It's a very difficult language to pair with R for architectural reasons, and it's really hampering BART machine's progress. So like I said, dependencies, dBART doesn't have any. BART depends on RCPP, and BART machine depends on RJava. And RJava is kind of a nightmare to install all by itself, let alone BART machine. So that's for what it's worth. dBART is not multi-threaded. BART is, and BART machine is also multi-threaded, but the multi-threaded we found is very, very buggy. It seems like it was like an afterthought, although it's got a yes there, I wouldn't use the multi-threading with BART machine. We have a predict function in BART, and so does BART machine, and dBART doesn't have that. Missing data handling. BART machine does handle missing data, but it basically just does the trick that I mentioned earlier. And like I said, a BART package does not, but I'm going to show you, I'm going to tell you how you can do it in BART in a far more sophisticated way than BART machine does it. Again, variable selection, we don't have variable selection in the package per se, but actually it's fairly trivial with some recent research that Rob has done to do variable selection, and hopefully I'll have time to show you that. Tree transition proposals. So dBART is the winner, I guess. They have 4, but BART and BART machine have 3. I don't know if we'll have time to talk about what that actually means, but certainly you can read Rob's original paper. It's actually fairly readable, surprisingly, and you can take a peek at that paper. After what he's told you today, you should be able to read that paper fairly easily and read more about the tree proposals. dBARTs and BART machine automatically do these things called partial dependence flots. I think it's kind of like a whiz-bang feature because it's fairly easy to do this without any assistance. So that's not, it's a no for our package, but I'm sure I'm going to show you how to do it. It's fairly trivial. So all 3 packages handle continuous and binary data, but only the BART package handles time to event data. dBARTs and BART machine, they do convergence diagnostics, but just for continuous outcomes. And as Rob has shown, it's actually quite easy to do it for continuous outcomes. So they're not really doing much, quite frankly. But we have developed for the other type of outcomes, we've developed some convergence diagnostics, and I'm going to tell you about those today. Thinning. For whatever reason, BART machine has no thinning, and it's actually a big problem, much bigger problem than you would think, because that means that on the Java side, they're creating a big object, and there's no way to make that object smaller because you can't thin the chains, and it will often crash your Java virtual machine, which gets very annoying very quickly. Cross-validation. So dBARTs and BART machine will do it automatically. BART, we don't. And I said I'm going to show you how to do it today, but I can't remember if that's true or not. We'll see as we go through that. Go through this. I don't remember if that's actually in the. Okay, so Rob has told you how BART works, and when I started looking into this, I was wondering, why does BART work? So there's been some research on ensembles and let's say prediction error. And prediction error is just the standard definition. Mean squared error is bias squared plus variance. And the game here is there's often a trade-off between the two. So consider the spectrum of trade-offs. Linear regression is on the high bias, low variance end. Single tree regression is on the low bias, high variance end. Totally opposite ends of the spectrum. And ensembles are in the middle, medium bias, medium variance. Now I was talking to Rob about this and he says this is not true. but according to the literature I've read, of course, now all ensembles are not created equal, okay? You can do very dumb things by creating an ensemble that doesn't work. So maybe we should say smart ensembles have nice properties. And as we've already seen, BART is in the class of ensemble models, which both theoretically and in practice have excellent out-of-sample predictive performance. And I just have some literature here that you can go and you can find some more information on ensembles, especially the book in the middle, Baldi and Brunac. They have lots of theorems that show why ensembles have such good performance from a theoretical perspective. Okay, so let's get to computing. First of all, people always tell me, wow, why are we doing multi-threaded computing? It's so hard. Well, Burroughs released computers that did asymmetric multiprocessing in 1961. If they could do that in 1961, you should be able to do it in your laptop today, and you can. They first came out with asymmetric multiprocessing, which is like, which we are all familiar with. That's like a GPU and a CPU doing different parts of the system. And then they came out with a full symmetric multiprocessing system back in 1962. So this is fairly old hat. And then there's something called Amdahl's law. Theoretically, they had figured out there's a big gain to multiprocessing, but there's a caveat, and I'm going to come back to that later. But to get it into our laptops took a lot of time. I think one of the practical challenges that was overcome was in 2000, AMD released what they called the AMD 64 architecture. So they had created chips that they were capable of native execution of 32-bit x86 legacy code, as well as new 64-bit x86 instructions. And they kind of caught Intel with their pants down. So that's why it's called the AMD 64 architecture and not the Intel 64 architecture. And then on the Linux side, Linux had symmetric multiprocessing, but it was fairly crippled until 2003. The Linux kernel 2.6 really unleashed symmetric multiprocessing or SMP support. And then a couple years later, AMD, still eating Intel's lunch at this point, created dual-core chips. 2 years later, they had 4-core chips. And in 2008, Intel finally catches up with their Xeon processors, and kind of the rest is history. Intel has sort of used their size and near monopoly status to take over. But AMD deserves a lot of credit for leading the way. Like on my laptop today, I can run 8 threads at a time. So it's fairly trivial to do it now. Just a few years ago, we could only do this with fairly expensive servers, but now everybody's laptop probably in this room can run at least 4 processes. Well, in some ways it's a lot easier on the hardware side, but on the software side, it takes it takes something to be on the software side to tell the hardware what to do. There's something called the Message Passing Interface, MPI, and Rob's got a paper in JCGS that shows how to do BART with MPI. So that's a little bit more sophisticated framework than we typically use. So I'm not going to talk any more about it, but it's out there. If anybody here is interested in high performance computing, that's there. Normally we use OpenMP for single nodes. This is used by the predict function. It's detected by the new auto tools when BART is installed. There's a C preprocessor macro that's defined if OpenMP is available. So it's underscore OpenMP. So this is something that that's detected when you install the BART package. Now, for my Microsoft fans, it's not available on Windows. New auto tools are not available. But now, almost everything you say in computing, there's some exception. So there was this project called SIGWIN, and they're still around. What they've done is they've taken the new framework and they've ported it to Windows. So it's there, but you're on your own. No support from CRAN or R. And also, Apple has got a black eye here. Apple currently does not support OpenMP either. However, again, there's an exception, and all the whiz kids can do it if they know how to install the open source version of Clang, and so you can get it that way. But there's no support from Apple or Microsoft. Now, message passing interface is generally used with several computers rather than one. If we're talking about a single computer, which for the most part is the way we do BART today, there's something called the Parallel R package. It's one of the standard packages in R. And again, Microsoft's just not having any luck with multiprocessing. Forking, which is the technology that the Parallel package uses, is not supported on Windows. And I don't know of a caveat there. I don't know if there's a workaround. I suppose SIGWIN is a possibility, but I'm just guessing. I have no idea. Okay, so and all of this is actually documented. If you just do !MC parallel, you can see basically what I just said, more or less. So we use forking for BART. So we've made wrappers. So like Rob was talking about the WBART package. So we've created mc.wbart, which does the multiprocessing version of WBART, and there's a bunch of these. You can also use the parallel package for the predict function, or you can use OpenMP. It just depends on. It's pretty much the same speed either way. So it just sort of depends on what your favorite parallel processing paradigm is. All right, so like I said, Windows not currently supported by R or CRAN, so it's Unix only at this point. Okay, so OpenMP, if you load the BART library, we've created a function that tells you whether OpenMP exists based on that C preprocessor definition that I was talking about. So it returns a 0 if OpenMP is not available and a 1 if it is. And forking, so if you load the library, the parallel library, there's a function called detect cores. So it returns 1 or more. And it's kind of an annoying function. Occasionally it returns NA. I have no idea what's going on there. When you're writing, if you're writing software that depends on detect cores, you just kind of need to be aware of that. Occasionally it just doesn't tell you. So like I said, on my laptop it returns 8. So BART is BART and MCMC in general are considered embarrassingly parallel. Well, what does that mean? That means it's fairly trivial to parallelize this. So like in black here, I have one long chain. So this is the way Rob's examples all were. He created one long chain of posterior samples, and that's how he did the computing. But let's say I wanted to do this all at the same time. I could do 5 of these all at the same time, right? So that's what they mean by embarrassingly parallel. But notice I have this line here. So this is the burn-in fraction. These are what's discarded. All right, so notice that Rob discarded 500. Well, now I'm discarding 5 times 500, right? So that's the burn-in penalty. So if we look at Amdahl's law, and I'm just sort of rewriting it, sort of deriving it here, the amount of work on the top over the amount of work on the bottom. The amount of work on the top is the amount of work done in one chain. The amount of work done on the bottom is the amount done by C chains. And B is the burn-in fraction, or what I call the burn-in penalty. So you get this, this relationship here. Look, I just circled it. Did you see me do that? I did the circle thing. Sorry. So in Rob's example, I think, he normally burns in about 500 for a continuous case. Normally for survival analysis, I burn in less just because of the burn-in penalty. So normally I only burn in like 250. And I also tend to go longer though. I usually do 10,000 and thin by 10, so I get 1,000 samples. So you can see what these curves look like. So if I throw 50 processors at it, the gain is about 25 times. So that's 25 times faster. And Rob, if he did it, it would be, it looks like about 7.5 times. But normally I'm over here on the curve. So they're fairly close when you're at 8 processors. It's about, I don't know, about 4 to 8 times speed up. And this is a big deal because 4 to 8 times can be a dramatic difference. Like typically, you can get it down to like 5 to 10 minutes, where it could be 4 to 8 times longer. So there's a substantial savings for calling just MCW BART instead of W BART. So it's worth it. Okay, but multi-threading does lead to some challenges. So the IEEE 754 specification says that every double precision number contains 8 bytes or 64 bits. So you can estimate the size of your needs. So if you have a matrix, which is n by n, the amount of RAM required is 8 times that. 8 times n by n. And bad things happen if you use all the RAM on your system. So if you use all the physical RAM, then the system will swap segments out to virtual RAM, which are disk files, okay? This will degrade performance rapidly and possibly crash the system. Because what happens is it swaps one segment out, realizes a few microseconds later that it still needs that segment, and it swaps it back in, and it goes into a death spiral. On Unix, you can monitor the memory used and the swap usage with top, but if you get into one of these death spirals, even monitoring it, you may not be able to kill the job fast enough. So what I tend to do is I start with a small example, I test my code, make sure that I'm not doing something silly, and then I scale up. Within R, you can determine the size of an object with the object size function. Okay, so R matrices are column major. So at the time that R came out, or I should say S, R is a descendant of S. When S first came out in the early 70s, C existed, but nobody was really using C for linear algebra. It was all in Fortran for the most part. So R, or S and R, are considered column major, which is the way Fortran does it, and C and C++ are row major. Well, what does that mean? Well, it has to do with the memory layout. So if you have your matrix that looks like this is the way R lays them out in memory. So, so R goes down the columns. See? So this is row 1, row 2, etc. So all of those memory addresses are adjacent to one another, and that's what's called column major. And why that ever got popular with Fortran, I have no idea, because it seems to me that C and C++ are just make more sense, so they go across the rows. So the adjacent memory locations are on the rows, and well, why does this matter? Because BART is written in C++, and we need to pass it a matrix that's in R. But this is pretty simple. All you do is you pass the transpose. So instead of passing A, you pass A transpose. However, R is considered a copy on write language. Well, what does that mean? That means it passes the objects by pointer. So there's no big double counting of the matrix. You're just passing a pointer to it. However, if you write to that matrix in the child thread, it creates a new matrix. So it looks like this. So if this is the parent memory space, and we have a big chunk like that, our A matrix, and then we have a child, well, the child just gets a pointer to A. Except if you pass A transpose, then what did you just do? You created another copy of A. So now you got two copies of A. If A is a big matrix, you could be in trouble, because generally you don't just have one child. Generally you have 7 or 8 or 30. So I'll call this one A transpose. So you have to be careful. So what is the trick here? Well, the trick is you don't do this, right? You just transpose A before you pass it to the child. And that's what we do. So we make A equal to A transpose, and then we pass that. No copies. All right, there's another aspect of multi-threading. So interactive jobs must take precedence over batch jobs to prevent the user experience from suffering high latency. Whoever's ever opened a terminal or opened an editor and started typing, and for us touch typists, we're supposed to be watching the mistakes we make as we make them so we can correct them. But what happens when the system's under high load? You're typing faster than you can see the characters. It gets very annoying, pisses people off. So what you have to do is, when you're running your jobs, make sure that you don't consume too much resources, because everybody else will hate you if you're sharing a system. If you're doing it to yourself, well, then that's your own problem, I guess. But in the tools package, there's a psnice function, and I'm just going to paraphrase from the psnice help page. So Unix has a concept of process priority. Priorities assign values from 0 to 39, with 20 being normal. And counterintuitively, larger numeric values denote lower priority. Adding to the complexity, there's a nice value, the amount by which the priority exceeds 20. Processes with higher nice values will receive less CPU time than those with normal priority. Generally, processes with nice 19 are only run when the system would otherwise be idle. So it makes sense that the BART package, when it creates children, their niceness is set to 19. Boy, I'm glad there's no questions. This is all so informative, or is this, am I boring you, or is it just so transparent? Or what's the problem? You sick of this already? You're free to leave if you want. Okay, so BART and MCW BART basically follow the same parameters. I guess it wouldn't make sense if they didn't, but there's a few differences. Let's see here. First of all, I should mention Rob didn't talk about keep every. So keep every, that's how you do the thinning. So by default, keep every is 1. So keep everything. So if you want to thin, you would make that 10 or 20 or something like that. But that's sort of beside the point. So what is the point here? Let me think. Well, look, notice what I have in red. So here you tell it how many cores you need. Also, the way seeds are passed in parallel is a little bit different than it is in serial computing, so you actually have to pass the seed. And as we talked about, these are matrices. And for the reason that I just mentioned, C++ wants a matrix, so we require these to be matrices. We don't want data frames or any other type of objects.
I have a question, Rodney. How many chains are you running in that
2.
example?
2.
So you put...
This is the default, by the way. You can make this is the default is 2.
Okay, so you put 1 chain on per core.
Yeah, that's right.
Okay, good.
That's the idea of embarrassingly parallel. The two threads don't have to talk to each other. All they have to do is be able to see the data, and they can. Okay, so it returns an object of type WBART, but it's essentially a list. As Rob's been showing you, it's basically a list.
We have another question.
What?
Mike, please.
You have to turn yours off.
Have you thought about or worked on having a core do more than one thread at a time?
Have I thought
No,
about
they
doing
can't
what?
do that. Never mind. I'm sorry. I spaced. I was thinking of having a core do more than one, but that's not possible. I wasn't.
More than one chain?
Yeah. I mean, you could stack them. But
Yeah, you could, but then you're back to the original
Right.
problem. So yeah,
Yeah.
so that's the whole idea, is you want to do as many as you can.
Yeah. Sorry.
That's okay. That's okay. I'd rather have questions than not. I feel like I feel like you're not here. Okay.
So just wondering, what is seed doing? Like if you have multiple chains working on different cores, like are they sharing the seed or?
Oh, I'm going to get to that. Yeah, that's a good question. Yeah. So just to finish up with this slide, like I said, it's a list, and what you get back is, and Rob's already talked about this, so on the columns, the rows are the MCMC draws, and across the columns are the different subjects. Okay, so as Rob mentioned, we have a predict function. By default, it only uses 1 core. Again, it returns an object of type WBART. Of course, the whole point of the predict function is you can put different objects in the first position, right? This is the way R does object-oriented programming. It keys off of what the first argument is, and it knows which type of object you're passing in it, and you give it different. You want it to do different things for different types of objects. So WBART is for continuous, PBART is for binary probit, LBART for binary logistics, SURFBART for survival analysis, CRISC for competing risks, and RecurBART for recurrent events. So it actually acts to do slightly different things for all of those, but actually WBART and PBART, it pretty much does exactly the same thing. right? Right, right, mister? Yeah, yeah. So my student Charlie helped me create these predict functions. So W bar and P bar do the same thing. So it gives you the same type of thing here. Well, I forgot to mention. So now, but now it's X test, right? Because these are different than the training settings. Because you've already got estimates at the training values. Now you want estimates somewhere else, right? So that's the point here. You can predict at any value. So you're going to get the same sort of matrix back. Okay. All right. So this is getting to your question about seeding. So it's kind of interesting the way parallel random number generation works. They used to think that just giving it each chain a different seed is all you need to do. But it's actually more complicated than that. Or I should say, it's more complicated to prove that's the right thing to do. Because what they're worried about is you have one process going like this, and one that starts over here. Actually, I'm going to draw it right on top. So let's say that one that starts over here, but over time coalesces with the other one. So, but just by choosing two different seeds is not enough. So it's more complicated than that. So you need a special class of random number generators, and the parallel package uses this kind. Does anybody speak French? I think it's liqueur is the way. Any French speakers? Is it that? Am I saying it right? Yeah. Well, that's the way I said it too. Okay. So, anyways, this is the proven, the theoretical way to do it. So again, the default nice is 19. Transpose is false because we're gonna give it a non-transpose matrix, and we're gonna transpose them here. Okay. So those are the arguments. You tell it to use liqueur, and then you set the seed, and then you have to call this function mc.resetStream. And once you do that, everything will work out the way you want it to. Okay, so you have one seed that controls the whole job, which is what you want. You don't want to keep track of 20 different seeds. So it's actually more convenient to do this. Not only is it the right thing to do, but it's actually more convenient. And then if nobody's done this parallel type of programming, I'm just going to go through this a little bit. First of all, if the number of cores actually available is more than the number of cores you've asked for, we just use the number of cores available. There's really no sense, if you talk to the computer scientists, there's really no sense of trying to use more cores than you actually have. It just doesn't help at all. It actually could degrade performance considerably. All right, so all you do is you just put this in a loop, and you call this MC parallel function, and then whatever you put in this function is what it's going to run on each of those different children. So we set the nice value, and then we call WBART, and we say transpose is true, because we're sending through transpose matrices now instead of non-transpose matrices. And this is to get out of the problem we were talking about earlier. You don't want to transpose them in the children, because that will just blow up the amount of memory you're using. And then here's a trick that most people don't use. What happens is all these threads are printing to the output, and it gets all garbled together. So you have to tell it to just only one of them can print. So I only allowed the first one to print. And then one other item. So all of these will be launched, but you need to get all that information back into the parent thread. So we have this MC collect function, and what it does is it takes all of those posteriors and it brings them back into one big list. And then something happens, and you get one chain. You get one big chain back instead of 8 separate chains. I was going to do a live demonstration, but I think I just talked too long, so I'm going to skip that. I just want to put a plug in. So in the package, what we wanted to do was we wanted to have people be able to call this from another language besides R. Right now, you can call it from R very easily, but Rob has put a lot of thousands of hours working on this code, and he wanted to be able to call it from C++, and some people want to be able to call it from Python or whatever. It's actually pretty easy to do. So right now in the package as it is, we've got it worked out down to a few bugs that we're going to fix very soon, but it actually does work. So not only does it work, but it's actually been a big help to us. It's far easier to debug the code in C++ with the C++ debugger than it is to debug it in R, because R sometimes will just crash and it won't give you any reason why, and it's very tricky. So it's actually much easier to debug it in C++. So there's a lot of benefits here to having the code be callable from other languages. And that's all I'm going to say about that. Well, any questions about this before I move on to the next topic? Okay, good. That's what I want to do.